Hello everybody, welcome back. We're going to continue learning about rational functions, and this is notes number 23. And today we're going to talk more about horizontal asymptotes. I want to give you a shortcut for finding them, and we're also going to learn about holes in graphs. So remember, a horizontal asymptote, which I like to denote with just the abbreviation HA, tells you what the y values are getting close to as the x values head toward infinity or negative infinity. So we also call this the end behavior. The horizontal asymptotes describe the end behavior of the graph. So really there are three possibilities. One possibility is that the horizontal asymptote will be the line y equals 0. And we've seen this on several of the problems we've done. We've seen things like this. I'll go ahead and draw a vertical asymptote in there. Okay? Now that's going to happen when the function is what I like to call bottom heavy. And what that means is that the denominator, is growing much faster than the numerator. So we would have something like y equals 1 over x plus 2 is an example, because if you put in very, very large numbers for x, you have a very small numerator over a very large denominator, so that's heading towards 0. Another example would be y equals x plus 1 over x minus 2 times x minus 3. So when you put in that very large number for x, like 1,000,000, yeah, you do have something close to 1,000,000 on the top, but you have something close to 1,000,000 squared on the bottom, and so that bottom is much heavier than the top. So what we're going to see is that, and you can imagine if you were to multiply the denominator out on this second example, what you can see is that the degree of the denominator, the degree being the highest exponent, is greater than the degree of the numerator. And that happens on my first example as well. The degree of the denominator is 1. The degree of the numerator is 0. So when the degree of the denominator is larger, it's bottom heavy, and it will have a horizontal asymptote y equals 0. So another possibility is that it has a horizontal asymptote, but it's some other line. I'm going to call it y equals k. So maybe the graph looks something like this, just as an example. So that line could be y equals 1, y equals 2, y equals -1, something like that. So this happens when it's not bottom heavy, it's not top heavy, but the degree of the numerator equals the degree of the denominator. Degrees are equal. So an example of that would be y equals x plus 1 over x minus 2. The degree of the top is 1, the degree of the bottom is 1, and the horizontal asymptote there is going to be the ratio of the leading coefficients. So the leading coefficients would be 1 over 1, 1x over 1x, so the horizontal asymptote would be y equals 1. Another example would be y equals 2x minus 4, or even 2x squared minus 4 over 3x squared plus 1. So the degree of the top and the degree of the bottom are the same. They're both 2. It's not top heavy, it's not bottom heavy. The degrees are equal. And the horizontal asymptote is going to be the ratio of 2 over 3. So the horizontal asymptote is going to be the line y equals 2/3. And then the third scenario is if there is no horizontal asymptote. So this should remind us of those polynomials that we were graphing in the last unit, or it could even have a vertical asymptote, maybe, but suppose it's doing something like this, going off toward infinity, or maybe off toward negative infinity. It's just not approaching a horizontal level. And this happens when it's top heavy. So the degree of the top is greater than the degree of the bottom. So an example of that would be y equals x squared plus 1 over x minus 2. The degree of the top is 2, the degree of the bottom is 1. So if you put in really large numbers for x, like a million, you have a million squared over a million. That's still really large. You put in a billion squared over a billion is even larger than a million squared over a million. So it's just going up and up and up and up. So what we can do is, and I'll just go ahead and write here, no horizontal asymptote. What we can do is summarize this, and this is going to be our shortcut for finding horizontal asymptotes. So here we have a polynomial, a rational function, I should say, p of x, and the degree of the numerator is m, that's the degree of the leading term, and the degree of the denominator is n, and the leading coefficients are a and b. So if m is less than n, then the degree of the bottom is greater, or the degree of the top is less, I could say. So this is bottom heavy. So the horizontal asymptote will be y equals 0. If m equals n, the degrees are the same, then the horizontal asymptote is going to be the ratio of the leading coefficients, so y equals a over b. And if m is greater than n, so it's top heavy. Those aren't official mathematical terms though, top heavy, bottom heavy, that's just kind of my language. There will be no horizontal asymptote. Okay, so that's one of our main ideas here today, and hopefully that helps streamline the process of doing one of these big problems. Now for the second big idea. Let's look at these two examples. We have g of x, which equals 1 over x minus 4, and we have h of x, which equals x plus 2 over x minus 4 times x plus 2. So, are these graphs going to be different? And if so, how will they be different? So one person might say, I don't think they're going to be different because if I just cancel the x plus 2 on the top and the bottom, then they're actually the same thing. So that's a good hypothesis. Now another person might say, well, I think they are going to be different because if I think about the domain of each one, the domain of g is x is not equal to 4 because that's where the denominator is 0. So we would have a vertical asymptote at x equals 4. But then for h, the domain is going to be x is not equal to 4 and x is not equal to negative 2 because those are both numbers that make the denominator 0 and we can't have that. So there would be two vertical asymptotes at 4 and at negative 2. So another person might say that. And that would be a good hypothesis as well. Actually, both are incorrect. And I want to take a look at both of these graphs on a calculator and show you what actually happens. So I've typed the functions in, and you'll notice that I put parentheses around my entire denominator for the first one, and an extra set of parentheses around my entire denominator for the second one, and parentheses around the numerator for the first one. Without those parentheses, the calculator is not going to have the right order of operations. Okay, the first thing I'm going to do is look at just the first graph. So I'm going to turn off the equal sign on the second graph, and it's only going to graph the first one. So I'm going to choose zoom decimal, which is going to give me a nice window for this graph. Okay, so this might be what we would expect. It has a horizontal asymptote of y equals 0 since it's bottom heavy, and it has a vertical asymptote here at x equals 4. Now let's take a look at the other one by itself. So turn off the first one, turn on the second one. Okay, it looks very similar. Horizontal asymptote, y equals 0, vertical asymptote, x equals 4. Notice there is not a vertical asymptote at x equals negative 2, but what is going on there? Do you see that little tiny gap? Now what if I graph them together? I'm going to turn the first one back on. I'm actually going to undo that process and go back because I want the first one graphed first. There we go. Okay, so the first one was blue, it was graphed first, and then the second one was red, it was graphed second. And do you see the little blue shining through? Because the red one has a gap. Well, we don't call it a gap, we call it a hole. There's a hole in the graph. There will be a hole in the graph at times when you have a factor that cancels, leaving no more of that factor on the bottom. So, if you had, let's say k of x equals x plus 1 over x minus 4 times x plus 1, you would have a hole at x equals negative 1. Now the way you would find the y-coordinate of the hole is you would cancel those, and then you would take your number negative 1, the x-coordinate of the hole, and you would substitute it in, so you'd have 1 over negative 5. Here's another example. Let's call it j of x. Let's say we had x minus 2 times x minus 2 over x minus 4 times x minus 2. So you can cancel an x minus 2, but notice that there's still an x minus 2 on the top. It is a hole. It's going to be a hole on the x-axis. So you're going to have a hole at the point 2, 0. Let's look at one more example. Suppose we have m of x, and let's say that this is x minus 1 times x plus 2 over x plus 2 times x plus 2. So you can cancel an x plus 2, but you still have an x plus 2 and it's on the bottom. So that's actually not going to be a hole. Whoops, I almost spelled hole the wrong way. It's going to be a vertical asymptote at x equals negative 2 if you have one of those remaining on the bottom. So we can summarize in general. And here we see an example where we have x minus a on the top and the bottom. Those cancel, leaving you with no more x minus a's. So there would be a hole at x equals a. And you would find the y-coordinate by putting that number into the reduced version of your function. For the second one, we see we have x minus a's that would cancel, but we would still have an x minus a on the bottom. And so we wouldn't have a hole, we would have a vertical asymptote at x equals a. And then for the third one, we see we have an x minus a we could cancel, but we still have an x minus a on the top. That would be a hole, and it's on the x-axis. Okay. So the next thing we have to do, I wanted to make a note. So you notice how all of the examples I gave you were factored. So these general examples are factored, and all the examples I gave you previously were factored. So if you get your problem and it's not factored, always factor it first and then reduce it. Reducing it is going to help you determine if you have any holes or not. And once it's reduced, then you can go through and do like the x-intercept, the y-intercept, all the other things, and it will be much simpler with the reduced form. So I'm going to end this video, and then we're going to have a part 2 where we do a couple of examples. We have example 1, 2, and 3. So stay tuned.